Good evening. My name is Kittson Hamill, and I am a sophomore computer science major in the Randall Research Scholars Program. I work under Dr. Jackie Gong in the SAIL lab at the University of Alabama on explainable artificial intelligence for decoding and modulating neuroplasticity. During my presentation, I will be going over background information, research goals of this project, the overall project process, my current results, and the next steps. During the pandemic, numerous organizations recognized the need for significant transformation in healthcare delivery approaches. This coincided with the advent of mobile and wearable healthcare technologies advancing to capture neurophysiological data from the human subject that wears it. This research is inspired by this, and it intends to investigate the potential for the application of at-home personalized treatment using artificial intelligence or machine learning for age-related motor function changes. I'd like to quickly go over some terminology before I go deeper into this presentation, because these terms specifically deal with what I've studied over this past semester. Firstly, EEG. It refers to electrophysiological monitoring method to collect EEG data or brain activity data. To do this, a scalp cap is placed over a human subject and electrodes are placed on it to capture electrical signals in the brain. In our case, we used a 64 electrode scalp cap. If you look under the EEG, there is an image there with 64 dots on it, each representing where an electrode was placed, and these correspond to channels that we collect data from. This data is then put into source localization. Source localization is where you identify where in the brain a particular activity originates based on the surface EEG recording. And if you look underneath source localization, the orange and yellow splotches on the brain show the estimated location of where an activity originated. For this project, the immediate research goals were to first develop deep learning algorithms that could analyze, simulate, and decode EEG data, and to create an algorithm that we would then use in the second research goal, evaluate algorithms in a lab setting to discover possible patterns of age-related locomotion changes. This is all to go towards our end goal, which is to create an app that pairs with a wearable device to collect neurophysiological data from the patient and send it to our cloud database. The patient wears this device and it contacts an app on their phone, which then goes to the cloud database, which computes and analyzes their neurophysiological data and returns possible patterns of human locomotion changes that could be used as a preventive measure in case of any chronic diseases that are onset. And this overall contributes to the current health technologies being used and provides a strategy for maximally preventing these chronic diseases in midlife adults. The process of this project can be broken into three main objectives. The first, which is the one I'm currently working on, is the data processing and machine learning implementation stage. In this, I am currently analyzing EEG data, and eventually it will go into creating a machine learning algorithm, which is used in the next stage, app development. The creation of this app is also the creation of our cloud database, and those will be used to create both the interface for the user and the database which stores our algorithm. This is then brought to our final stage, the on-phone artificial intelligence. So the wearable device that the human subject wears connects to their phone, and it sends their neurophysiological data to the database to get analyzed and return any possible signs of locomotion changes. This semester and the next semester, I am focused on the first step of that three-goal process, and it can be broken into three stages. First, EEG data analysis and source localization, which then goes into multi-scale modeling. Multi-scale modeling is taking EEG data and IMU data, or movement data, to create a full-scale model of a human in motion. And then that goes into machine learning, which is used to create our algorithm to find these patterns in locomotive changes. This semester, I specifically focused on source localization and EEG analysis. To do this, you have to use processing algorithms like S-Loretta, E-Loretta, and DSPM to return source localization results. And to do this, I use Python as my primary coding language. and used the MNE Python package, which is specifically tailored to analyzing and visualizing EEG data. I did this in the Anaconda Spider environment, and I also used an additional package, FreeSurfer, for supplemental visualizations for source localization. The test subject data was collected on a volunteer prior to me entering the lab, but the data was collected on multiple body parts over a period of 160 seconds, and my analysis focused on the shoulder data specifically. The limbs alternated between extending and flexing, and the fingers alternated left and right tapping every 5 seconds. These finger taps, extensions, and flexions were captured as event triggers, and both EEG and IMU data were collected. For my current results, I was able to analyze and model the EEG data that was recorded in our lab using MNE and FreeSurfer, as you can see in the following slides. So these 3 images show the brain activity of a period of 5 seconds for each of the 3 triggers: extension, flexion, and finger tapping. The dots on the heads are representative, once again, of the placement of the 64 electrodes on the EEG scalp map, and the activity of the brain is determined by the color saturation on these images. You can see in both extension and flexion at 1.6 seconds, the most saturated color was in the upper right, whereas at any other time period, there was less saturation. Finger tapping, however, had increased activity across the entire 5-second period, with color saturation deepening on the right side of the scalp in the images across the seconds, and at 5.2, it had the most activity on the right side. This data was then put through the 3 different processing algorithms, E-Loretta, S-Loretta, and DSPM, to find the estimated source of the EEG data. The graphics are taken at the 3.4 second mark, and the EEG data shows high activity at the orange and yellow splotches on the brain. E-Loretta and S-Loretta had similar results with predominantly right side activity, whereas DSPM had more frontal brain activity. As you can see, it doesn't have as much on the left side of the image. This can be seen further in the resulting graphs. These graphs show the levels of brain activity for the left and right hemispheres over a period of 5 seconds. The left hemisphere is the blue line, and the right hemisphere is the orange line. And looking at E-Loretta and DSPM, you can see that the left hemisphere activity and the right hemisphere activity stay almost on top of each other, a bit more separate on the DSPM, but they're still pretty much together, whereas S-Loretta has greater right hemisphere activity, much greater compared to the other 2 processing algorithms, and also compared to the left hemisphere. My next steps are to remove data artifacts or data points that skew the data and make it unusable, and verify my results against other people in my lab to make sure that the results are actually accurate. To do this, other people in my lab are using different processing algorithms and softwares, so by making sure our results are similar, we'll ensure that the data is accurate. And next, multi-scale modeling, which is taking the EEG data that I analyze and the IMU data that was also collected from the human subject that is being analyzed by a different group in my lab, and creating a full multi-scale model. And then finally, collecting more data on a more diverse population of human subjects to strengthen our algorithm. I'd like to thank Dr. Jackie Gong for his mentorship over this semester, and I would like to open the floor for questions at this time.
So can you explain the difference between the 3 algorithms, the S-Loretta, E-Loretta, and DSPM?
So the main difference between the Lorettas and DSPM is their normalization, their process of how they normalize the data. DSPM is based on noise covariance, whereas S-Loretta is more focused on a theoretical covariance data that it creates from a minimum norm. So it doesn't use the noise covariance as its normalization. But E-Loretta is the same, but the only difference between E-Loretta and S-Loretta is that E-Loretta doesn't use a linear imaging model to create its algorithm, which is the only difference. They're still in the same Loretta family, though, so they're pretty similar.
As far as like the project goals as a whole, can you go a little bit more into kind of what populations this would be used for, and kind of like what issues it might address?
So this can also be used, from my understanding, to help in rehabilitation for populations that have possibly undergone strokes and possibly undergone any other chronic disease of some sort that might benefit from having their neurophysiological data analyzed to create a better rehabilitation process during their physical therapy, because having that tailored to how their brain works helps them better improve their mobility.
I was wondering why you chose to use M&E and if there are any other software packages used to analyze EEG data.
So there are many software packages that are commonly used, such as Brainstorm and Nutmeg, among just to name a few. But I specifically used M&E because their inverse method for creating the source localization is different across these packages. So whereas M&E uses S-Loretta, E-Loretta, and DSPM, Brainstorm, for example, only uses a dipole modeling S-Loretta and DSPM. I wanted to look at E-Loretta as well, though, because it's one of the most recent releases from the Loretta packages. So I decided to use M&E because it was the one that fulfilled this.
Great. Good job, Kittson. Thank you.